Welcome back. It's time for our second talk, which will be given by John Shareshian, who exists, who's here in person, which is great. And John's talk will be on invariable generation of finite simple groups by two elements of prime or prime power order. Thanks, John.
Thank you, Cheryl, very much. Let me thank all of the organizers. It's, of course, a great pleasure and to be here and an honor to be able to speak to you. In particular, it's a really great pleasure for me to participate in anything that honors Michael and Bob, who I admire in many, many ways, both as mathematicians and as humans. I'm really thrilled to be here. So I would like to speak about joint work with Bob Guralnick and Russ Woodroofe from the University of Primorska in Slovenia. And this is about invariable generation of simple groups. So let me just start with definition. So G is a group, always finite, and take some subset. And this generates G invariably. If, well, I just replace each xi by an arbitrary conjugate. And I still generate G. Is my writing sufficiently large and legible? Okay, so this is invariable generation, right? I have some subset of my group. I replace each element of the subset by an arbitrary conjugate. These G's don't have to be the same, anything like this, and I still generate G. And so the theorem I want to start with my understanding is that this was proved simultaneously by two groups of people. Many of whom are present. Right. If K is simple, then it's invariably generated by two elements. There exist X, Y in K that generate K invariably. Okay. So what the talk is whether we can place restrictions on X and Y in these circumstances. So let me write the questions that I aim to address. We're well along in addressing them, but our work is ongoing. So here's our question. Can we choose X and Y so that, well, I guess I have three questions. A, X and Y are both prime. Both, sorry, have prime order. One of them has prime order, and the other is a prime power, has prime power order. Or the weakest one I want to consider is that they both have prime power order. And let me, this is group theory, so this won't bother you. I'm usually working on combinatorics, but can we choose, say, with finitely many exceptions? Yeah, exactly. Thank you. That is ambiguous, right? And so these are the questions, right? And the answers are varying. And so what I intend to do is examine, use the classification, examine first alternating groups, then sporadic groups, and then finally groups of Lie type. I guess it's really fun for me to talk about this here because especially in the examination of groups of Lie type, well, working on this allowed me to engage more deeply than I had before with the amazing work of many people who were present. For the classical groups, of course, we start with Michael's work on maximal subgroups. Let me remark that this is really a question about maximal subgroups, right? Because what we're asking is, can we choose X and Y with these properties, right? So that no maximal subgroup of K hits both the conjugacy class of X and the conjugacy class of Y, right? That's the same question. So this is a question about maximal subgroups. This is, the toughest part, as we'll see, right? Well, the alternating groups are very tough. The toughest part, as we'll see, maybe will be the classical groups, where the work of Michael and all the work that followed it of many people who are present are essential. Okay, so far so good. Well, let me say that when a question about maximal subgroups comes up, as many of you know better than I, that there are possibly two obstacles, right? The one is that a ton is known about maximal subgroups of simple groups, but not everything, right? And surprisingly to me, maybe as an outsider, was that's usually not the real problem. If you consider, say, the Guralnick-Thompson conjecture on branched coverings of Riemann surfaces, or conjectures of Bob that followed that. The problem is not that you don't know everything. The problem can be that some things you understand very well actually are hard to analyze in the context of the problem at hand. And that's the case here. And so let me start with symmetric groups or alternating groups. So the answer to A is no. Right? In fact, there are infinitely many n's for which the alternating group AN is not generated invariably by two elements of prime order. Right? Say n is 2 to the k, right? And now, right, we consider AN. Okay, so what's the problem? So X and Y have prime order. They're supposed to generate invariably. It means one of the primes is 2. Because if I take an element of odd prime order in A2 to the K, it's got a fixed point. Right? Can't act without fixed points, and therefore, right, AN minus 1 will contain both a conjugate of X and a conjugate of Y if both X and Y have odd order. So you can't win that way. So then, X is 2, and in fact, X must be fixed point free. Right? Otherwise, you lose. Right? There's some AN minus 1 containing a conjugate of X and a conjugate of Y. Okay, now, right, Y now certainly can't have order 2 because then X and Y would generate a dihedral group. Right? Y has to have a unique fixed point for the same reason. If Y fixes 2 or more points, then some conjugate of X and some conjugate of Y will live in the stabilizer of a 2 set, right? And so you lose again. So Y has a unique fixed point. But now you stare at this, and some conjugate of X and some conjugate of Y, right, then generate a subgroup of the affine general linear group. Right, because Y is a power of a generator of a Coxeter torus in the general linear group, a Singer cycle. Right, Y is a power of a Singer cycle, X is a fixed point free involution that lives in the translation group. Right? So you're out of luck, right? There are infinitely many n, right, for which A doesn't hold. Okay. All right, but in fact, B, maybe. We don't know any counterexample. And this leads us actually to an interesting number theoretic problem. So what's the issue here? Right, so we want to choose X and Y like this, such that no conjugates, that every maximal subgroup misses some conjugacy class. Well, the real issue is whether we can choose X and Y like this, such that when I choose arbitrary conjugates, I generate a transitive group. Right? The primitive groups will run away and hide, and the transitive but imprimitive groups can be gotten around. The idea is maybe I should pick Y to have prime order, which is bigger than n over 2. So I take some p cycle for p between n over 2 and, like, instead of n, like n minus 3 or something like that, to avoid primitive groups. And then I would like to take X having order dividing n, we're in an, right? And say, for instance, having the same orbits as a CLO subgroup in which it lives, right? And you can do that, right? Or you might have to split one orbit in half if you happen to have chosen the prime too, right? So the real issue is whether we can choose X and Y to generate a transitive group, right? And so, right, a close question, a weaker question, can we choose primes P and R? So here we're given n. Right? Can we choose primes P and R such that the group generated, I say what these are in a second, is transitive for all, well, CLO subgroups? Instead of just looking at elements, look at CLO subgroups. So this is a much weaker question, but in fact, it's the guts of this problem. That there's very little difference between solving this problem and this problem. Right? I just replace elements of prime of power order with CLO subgroups. Right? This question's open, right? And it's equivalent to the following question. That every non-trivial binomial coefficient, right, is divisible by at least one of P and R, right? Because an intransitive maximal subgroup will contain both a CLOP subgroup and a CLOR subgroup if and only if its index is not divisible by either P or R, and its index is n choose K if it stabilizes a K set. Okay. So this is the problem, and you could ask this problem, right? Lots of combinatorialists might come up with this problem. I should say that a result of Kummer, right? You might expect here that the answer is no. The reason you might expect that the answer is no is, a very old theorem of Kummer asserts that the GCD of all of these is larger than 1. In other words, it is 1 prime that divides all of these simultaneously exactly when n is a power of that prime. Right? It's not too hard to see when primes divide binomial coefficients, right? And so, if you're asking for 1 prime that divides all of these, the answer is generally no, not at all. So now we're asking whether there's 2 primes such that each one of these is divisible by at least one of these. Right? This sounds unlikely, but in fact, it's at least close to true. So right? The first thing is yes for n up to 10 to the 15th. So Russ is a magician at programming, and he got this far, right? There do exist primes up to 10 to the 15th, and now there's a theorem. So I should say that Russ and I some years ago proved this, assuming the generalized Riemann hypothesis. But here's a theorem of Joni Teravainen. Answer to, in fact, the stronger problem, A, is positive on a set of asymptotic density 1. So, like many problems like this in number theory, I don't know, this doesn't have to be true, but if it's not true, it's going to be very hard to find a counterexample. All right, so this just means I pick some very large n, I count all the numbers up to n for which this is true and divide by n, and that has limit 1, right? No, A, in fact. Yeah, so in fact, I asked this weaker question just to illustrate that even this weak question, right, it's not so obvious you should get a positive answer, right? But even this hard problem, right, has a positive answer usually, right? It's just certainly not always, right? This is a very sparse set, right? So this is true on a dense set. What? Oh, well, here we have infinitely many no's. With finitely many exceptions, can we choose XY? No, because here are infinitely many exceptions where I fail. So sorry. So thank you for asking. It's obvious this was a bad thing to write, right? But this is what I mean. Okay. So that's that, right? But you know, you have to do analytic number theory to get anywhere with this problem. And I don't know how to solve the whole problem. Analysis, you know, doesn't solve the whole problem. It solves it usually. Okay, so sporadic groups. Well, of course, finitely many exceptions is meaningless, but we have a complete answer. So for M12, C fails. Now here we're not talking about exceptions. You cannot generate M12 invariably by 2 elements of prime order. For M11 and M24, A fails and B is okay. And for all others, A is fine. Okay, so of the 26 sporadic groups, 23 are generated invariably by elements of prime order, and these 3 are troublemakers. And this is a real troublemaker. You cannot get all simple groups this way. Okay, and so now the Lie-type groups. Right, so these, of course, require some group theory. And we have a theorem. B, yes, with finitely many exceptions. And a conjecture. C, yes, with finitely many exceptions. So we're well on our way here. I don't want to say we're well on our way to proving it because we might get surprised, but we're well on our way to settling it. There are some A, yes. Thank you, Percy. Yeah, that wouldn't.
You know we're watching.
Yes. right? So we hope this is true, right? And there are some sticky cases. I would say the nastiest cases that we're still working on are the orthogonal groups of plus type and the symplectic and orthogonal groups in even characteristic. I believe everything else is under control, possibly unitary groups of even degree, but I'm not too worried about those. So we're close. The exceptional groups of Lie type, or the non-classical groups, can be handled directly. There is sufficient knowledge of all the maximal subgroups. What do you do? Let me just say, so I don't want to talk in too much detail about this. What you do is pick a Zigman prime for a large exponent. And let me put exponents in quotes, right? What I really mean is the order of the given group is a polynomial in the field size. And when I say exponent here, what I mean is I look at some cyclotomic polynomial that divides this polynomial that tells us the order of the group and take a large, right? It's cyclotomic polynomial for one of the larger possible exponents in that sense. So when the group is untwisted, these are the actual exponents according to the usual definition, but when the group is twisted, that's something else, right? Right, and then either pick another or the characteristic. Right, this is the scheme, and it depends, on which particular class of groups you have, which is going to work. Right, and so what are the kind of obstacles? Well, if you pick the characteristic, right, you're trying to pick a unipotent element. If you're aiming over here, right, then you can pick a regular unipotent element or something close where there are very few fixed points, right? What kind of subgroups do you have to worry about over here is typically like stabilizers of non-degenerate subspaces of very, very small dimension and extension field subgroups. That's typically what you have to worry about here. And then, of course, almost simple groups that don't stabilize everything, right? And so you need to avoid those. And now, right, if you pick, a regular unipotent element, right, this is great over here, but it's not great over here. So the kind of questions that arise is if I pick a unipotent element with very small Jordan blocks, but not of size 1, because you don't want to stabilize a non-degenerate subspace, right? Can both an element like this and a unipotent element with small Jordan blocks lie in a subgroup that doesn't lie in one of the Ashbacher classes? And in particular, can it lie in a cross-characteristic but not co-prime characteristic subgroup? And so, in fact, the kind of questions that Kip was addressing in his talk about what do elements look like in the image of the Ray representation, right? Once we can kind of get enough of a handle on that, I think we should be done. Right? So that's what's at issue. Okay. So we're in pretty good shape. And do I have till half past? Is that correct? Let me end it. There's an application. So I remember one time, first time I met Bill Cantor, and he asked me and he said, I heard you're a group theorist. I said, I'm doing this. And he said to me, you're not a group theorist, you're a consumer of group theory. And this was accurate, right? Yeah, it was unsurprising and accurate, right? And, so why would a consumer of group theory be interested in this? So let's take G as an arbitrary finite group. And we'll define this, what's usually called probabilistic zeta function. This is the sum over all subgroups H of G of the Mobius function on the subgroup lattice. We make Percy very happy. Okay. Over the index to the S power. So this is a finite Dirichlet series, if you like, into which you can substitute any complex number. And in fact, this was studied maybe closely first by Nigel Boston and by Avi Noman. When you plug in a positive integer, it gives you the probability that S elements of G chosen uniformly with replacement generate G. And that's sort of the purpose. This is the maybe most interesting first example of Mobius inversion, right? But you could plug in any other things. And so you could ask, what's this? And maybe, right, this is an example of what combinatorialists call reciprocity. For instance, if you look, say, at the chromatic polynomial of a graph, right, you plug in a positive integer, it counts proper colorings. You plug in -1, it counts something, namely acyclic orientations. And so this is in the same spirit. And well, at least up to a sign, this is the Euler characteristic of something. So this here is an order complex. Sorry, I don't have time to define all this, but those of you who know these definitions, this is the poset of all cosets of all proper subgroups of G, right, ordered by inclusion. This is an observation of Serge Bouc. Right. Now, Ken Brown studied this very closely. Right. And what he observed is no examples where this is 0. He found no examples. And he asked whether this Euler characteristic can ever be 0. So this is the reduced Euler characteristic of some simplicial complex, right? And you want to know whether or not it's 0, right? And well, why should it be 0? It should be 0 because this simplicial complex is contractible, right? So this question remains open, whether this can ever be 0, despite some heroic work by Massimiliano Padacini, who was a student of Andrea Lucchini. This question remains open, but here's a theorem we can prove. This simplicial complex is not QA cyclic. Russ and I proved earlier that it's not acyclic in characteristic 2. The reason you might ask what this has to do with this is you use Smith theory. You use a theorem of Oliver that says that certain kinds of groups cannot act without fixed points on acyclic complexes, and you use the invariable generation to produce certain kind of groups that act without fixed points on complexes closely associated to these. So this is an application that I think is pretty interesting. I should remark, well, we didn't finish. You don't need anything this strong, right? You just need one of these elements to have prime power order. The other can have arbitrary order, and this is true. So, you know, we wanted to prove the best possible thing, but for this application, which is at least where Russ and I started before we approached Bob, was what we were really interested in. That you can show that we still can't show the Euler characteristic can't be 0, but this complex here is never acyclic, in contrast to, say, something like a Quillen complex or a subgroup lattice or other things that typically arise in group theory, right? This is always interesting. Okay, thank you very much.
Questions? Comments?
Yeah, sorry. The reason this is an Euler characteristic, and that's why. And once you know that this is an Euler characteristic, it's not too hard to derive this. I should say, right? Combinatorialists know Hall basically for the marriage theorem and Mobius inversion. And whenever I talk to a combinatorialist, I say, Hall was a great group theorist, right? And of course, he was a great combinatorialist also. And thank you for pointing that out.
I see your hand at the back of, I can't see who. Emilio. Can you speak up, please?
So we have a sum of which involves a whole bunch of Mobius numbers. And this thing here, when you take the coset poset, this coset poset is essentially the union of a bunch of cones over the subgroup lattice, right? But you don't know how those cones are glued together, right? So you're allowed the trivial subgroup in this definition, right? So you have every element at the bottom, and above every element is a picture of the subgroup lattice, right? So you get a bunch of cones over here, but they're glued together in a complicated way, and knowing something about some of these is not sufficient. Right? That's basically the problem. I should say there is a product formula when G is solvable. This goes back to long before this was studied. Right? This is Geschurtz. Right? When G is solvable, the product formula. These numbers are mysterious when G is not solvable. They're transparent when G is solvable.
Thank you, John. Now, before we thank John